Let me switch it on. Okay, so it's a pleasure to welcome Dario Prandi. We'll give a talk with title Point Interactions for Three-Dimensional Sub-Laplacians.
Yeah. Okay, so thank you very much, Luca and Enrico and Ugo and Mario and all the organizers for this invitation. So I'm going to talk about a recent work with Riccardo Adami, Ugo Boscaini, and Valentina Franceschi. And okay, so we're going to talk about point interactions for three-dimensional sub-Laplacians. So let me start with a little bit of motivation. So our main motivation is, well, it has been since a long time, how does the geometry affect quantum particles on a manifold? So let me say, in a very general point of view, we start with a manifold with some geometric structure, for example, a Riemannian metric. We consider a measure, for example, the Riemannian measure, and then this allows, these three ingredients allows us to define a natural diffusion operator. Okay, that is, for example, in the Riemannian case, is the Laplace-Beltrami operator. So this is a non-positive symmetric operator that is defined, well, we start by defining it on smooth compactly supported functions and acts on L2. So once we have this natural diffusion operator, we can write what is the evolution of a quantum particle on M. So a quantum particle is just an element of L2 of M, eventually normalized, and it evolves according to the Schrödinger equation. Okay, so it's this equation here. So our main object of interest, the thing we want to study is how this evolution is influenced by the metric structure, the geometric structure that we have. So how the upper half of this slide interacts with the lower one by means of this natural diffusion operator. So the first thing one can look at is the so-called quantum confinement. So once we have this Schrödinger equation, okay, we could ask if it is well posed. This is the first question. And in particular, if it is well posed without specifying any type of boundary conditions. So here I did not write any boundary condition. First question is, when is this something that makes sense? And more or less, this is answered by the Stone's theorem that tells us that this evolution is indeed well posed and is a unitary evolution as we would like, if and only if our operator delta that we defined a little bit above is essentially self-adjoint or self-adjoint if you prefer. Okay, so now the question is, which kind of geometry allows for an essentially self-adjoint diffusion operator? So from the Riemannian point of view, this is a very old question. It dates back, the answer, at least for a complete Riemannian manifold, dates back to Gaffney in the 50s, that showed that if the manifold is complete, then we have indeed quantum confinement. That is, the Laplace-Beltrami operator is indeed essentially self-adjoint. So we have only one possible evolution, one possible Schrödinger evolution without any boundary conditions. Otherwise, if we are not in the complete case, well, then things becomes a little bit more difficult. We can have to impose boundary conditions, for example, where we are in open sets of Rn with a smooth codimension one boundary. But more in general, this question has been investigated by, for example, in the Euclidean case, by Nenchu, or by myself with Luca and Marcello Seri in the Riemannian case, where we show that the measure can have indeed an influence there. Same thing happens for sub-Riemannian manifolds. So in sub-Riemannian manifold, when the manifold is complete, we have indeed quantum confinement, and this has been shown by Strickarts for every smooth volume. However, if the manifold is not complete, or if also the volume is not smooth, well, this has been studied by Ugo with Camille Laurent, and we expanded a little bit on that with Valentina and Luca, and we found some necessary conditions to have, some sufficient conditions, sorry, to have quantum confinement in these settings. Now, what I want to talk about in this talk, on the other hand, is a little bit more refined condition, a little bit more refined topic, let's say, that is the one of point interactions. So from the physical point of view, even if you know that you have quantum confinement, you could be interested, you are interested oftentimes to consider potentials that are concentrated at a single point. So at least from a formal point of view, you do that by taking your Schrödinger equation and adding a potential that is essentially a Dirac measure multiplied by some constant. And now the natural question at this point is, when does this kind of interactions exist? Now, mathematically, of course, at least in the setting I described above, this doesn't make any sense, because now we have some distributional equation, while we would like our equation to be well defined in L2. So what one does is that, at least, well, you have various different ways to do that. But what we are considering is to express this type of point interactions simply as the self-adjoint extensions of your diffusion operator, when you take, instead of its domain to be, instead of just compactly supported smooth functions, you restrict it to compactly supported smooth functions whose support does not touch the point where you want to put your potential. So this means that, well, it's pretty straightforward to see that if you interpret this kind of interactions in this way, they can exist if and only if this operator is not essentially self-adjoint. Indeed, if the operator with this domain is essentially self-adjoint, then it has just one self-adjoint extension that has to coincide with the one that you would get without removing this point. And so you do not change the quantum evolution at all. Okay, so this is the starting point. And well, this has been answered, at least for, well, in the Euclidean case a lot before, but in the 80s by Yves, showed that on a Riemannian manifold, actually, if the dimension is smaller than 3, then this pointed operator is not essentially self-adjoint, while if the Riemannian manifold is complete and the dimension is bigger or equal than 4, then this operator is indeed essentially self-adjoint. That means, from our point of view, that point interactions exist in dimensions, for example, 3 and 2, but does not exist in dimension 4 onwards. Now, this is not just, just a physical question. Let's say it's also a deeply mathematical one, because it's connected with the fact that smooth compactly supported functions whose support does not touch the point are indeed dense in H2 of M, where I'm defining H2 as the via the graph norm of the Laplacian. Now, this is the result for the Riemannian case. And as I've said, we can restate it by saying the point interaction exists if and only if the dimension is smaller than 3.
Is a question okay?
Yeah, of course.
That if and only if about H2 of M, is that only in the dimension 4 and bigger case, or is that in all cases?
Yeah, okay. Let's say the essential self-adjointness can be reinterpreted with this property, let's say.
Thank you.
But I will be more precise about this later anyway. So when we, what do you say? Yeah, so what happens in the Riemannian case is that when we, starting from dimension 4, points become too small. So they are too small to put some interactions there. Quantum particles do not see these points because their codimension is too big, okay? And then this begs the question of what happens in the sub-Riemannian case, because in the sub-Riemannian case, as you well know, the topological dimension is always smaller than the Hausdorff one. And in particular, so we want to focus on what happens in the 3-dimensional sub-Riemannian case, where we have the topological dimension equal to 3. That is not enough to get to ensure that point interactions do not exist in the Riemannian case, while the Hausdorff dimension is at least 4. That should ensure no point interactions in this case, okay? So this is our question, the main question we are posing. And indeed, what we show is that if we start from a 3-dimensional complete sub-Riemannian manifold with a smooth volume omega, and we pick a point on this manifold that is what we will call contact point. So it is a point where we just need one bracket to generate all the tangent space. Then the sub-Laplacian with domain compactly supported function outside this point is indeed essentially self-adjoint. So we do not have point interactions in this case. And here I should say that when I speak about a complete sub-Riemannian manifold, I implicitly am excluding the Riemannian case, of course. Otherwise, this result is false. Now, what I'm going to do in the following is just to focus for most of the talk on the case of the Heisenberg group, that is the model case, as you well know, of 3D dimensional sub-Riemannian manifolds with this property at all points. I will show how to prove this result, or at least give an idea of the proof of this result in the Heisenberg case. And then I will discuss a little bit how to extend it to get the full theorem. Okay. So let me just go to the Heisenberg group. So now I will just fix some notation, essentially, because everyone here probably knows very well these things. So the Heisenberg group is simply the Euclidean space, the R3 space, endowed with a non-commutative group law that we have here, and on which we put then the sub-Riemannian structure defined by these two horizontal vector fields. Okay, these vector fields are left invariant vector fields with respect to this group law, and their commutator gives us the third missing directions, that is dz. And also the natural measure here, so I will not discuss at all any possible choice of the measure, is simply the Haar measure, because we are in a group, in a unimodular group, actually, that is the Lebesgue measure. Okay, very well. So how do we define the natural diffusion operator here? So we pick a metric on the distribution. So our distribution is just the linear span of the two vector fields x and y, and we pick a metric that makes them orthonormal. Then we have a well-defined sub-Riemannian gradient that is defined via the metric, and is simply the derivation along x and the derivation along y. And this allows us to define the sub-Laplacian as an operator whose domain are smooth compactly supported function on the Heisenberg group that acts on L2 and is defined as the composition of the divergence with the gradient. And here I want to stress that we have that in the definition we have the gradient that is a metric component, is something that comes from the metric that we chose, and the divergence that is something that comes from the measure also. Okay, but in this case, since x and y are divergence free, what we get is simply the sum of square operator that we all know, I guess. Now, this operator is very nice, is very well behaved, well, at least not so very well behaved, but a little bit, because it is invariant under left translations. And this fact that it's invariant under left translations will allow us from now on to just focus on point interactions in the origin. I will not pick any point in the Heisenberg group on which to put my potential. I will just put it in the origin, since up to translation, everything is the same. And we know that this operator is hypoelliptic. That is the solution of the Poisson problem with data in C infinity is going to be C infinity, and it's actually a little bit more, because even though it is not elliptic, it is sub-elliptic. So we gain one derivative, not two, as we would expect from a second order operator, but at least one. And also there is another result by Strickartz in '86, where he showed that, well, a consequence of which is that this operator on the domain that I picked is indeed essentially self-adjoint. So we have a well-defined evolution of quantum particles, for example. Now, on this structure, we have also a metric, because we have that the commutator of x and y equals z, so it's the missing direction. So we have what is called the Ormander condition. We can endow then the structure with the Carnot-Carathéodory distance. This is a distance, it induces the same topology as R3, but it has a very strange shape. Balls have a strange shape, they have singularities, and what's gonna be interesting for us is that they are not isotropic. What does it mean? Well, this means that we have a family of dilations that I will call delta lambda, that are anisotropic dilations, because you see we are multiplying x and y by lambda, but we are multiplying z by lambda squared. But everything behaves well with respect to this dilation. So the distance is one homogeneous, the Laplacian is, the sub-Laplacian, sorry, is two homogeneous, as we would expect, but the measure is, the measure of a dilated set is lambda to the power of 4, the measure of a set. Although we are in topological dimension 3, measure scales with the 4th power. So this is a byproduct essentially of the fact that the Hausdorff dimension, that is also homogeneous dimension in this case, is equal to 4. Okay, so this will play a role in the following. Now, as I was saying, our main question is the sub-Laplacian now essentially self-adjoint on R3 minus 0? The two dimensions that we have to consider are the topological one and the Hausdorff one, that are 3 and 4. And what we get is, as I've already said, yes. So the sub-Laplacian is going to be essentially self-adjoint. Now, this is not at all surprising. I mean, at least for me, it wasn't surprising, in the sense that we started working on this. We expected this fact to be pretty trivial to prove, essentially due to this dimension, to this Hausdorff dimension being equal to 4. However, it turns out it's not so straightforward, because we have some genuinely sub-Riemannian phenomena that enter into play, and I will try to explain to you a little bit now what goes wrong with the usual way of proving this thing. So our first approach was to try to obtain this result via Hardy inequalities. So what you can show, actually what we showed with Valentina and Luca, was that in order to prove that your sub-Laplacian on the pointed domain is essentially self-adjoint, it is enough, it is sufficient to show that you have a Hardy inequality with a constant that is bigger or equal to 1. So here I wrote a Hardy inequality that is a sub-Riemannian Hardy inequality. So you see here we have the sub-Riemannian gradient, and here on the right-hand side, sorry, we have the Carnot-Karateodori distance from the origin. Okay, so one would expect an inequality like this to be true, and indeed, what happens is that this same theorem holds in the Euclidean case, and in the Euclidean case, it gives us the correct answer. Okay, because if we try to find an Euclidean Hardy inequality, well, we know that we can find it with constant n minus 2 over 2 squared that becomes bigger or equal than 1 exactly when n is bigger or equal than 4. Okay, so this was our first try. Unfortunately, it doesn't work. Why? Because, well, the literature about Hardy inequalities in the Heisenberg group is pretty extensive. So let me just recall some results. So we have, the first one was by Garofalo and Lanconelli in the 90s, where they're working in Hn, so in the nth Heisenberg group, where you just have one vertical direction and two and n couples of horizontal vector fields that behaves like x and y. And here the homogeneous dimension is 2n plus 2. And they show that we have indeed an Hardy inequality, something unhardy-like inequality, let's call it, that is sharp with a constant that is exactly the generalization, let's say, to the setting of the Euclidean constant. But unfortunately, what you get as a weight is not the distance from the origin, is something expressed in terms of the Korany norm. So it's just the Korany norm divided by its gradient. And this cannot work with respect to our theorem. So what is the problem here is that if we just had the Korany norm, we would have no problems. But the problem is that the gradient of the Korany norm goes to 0 on the z-axis. And so this fact does not allow us to exploit this Hardy inequality in order to obtain the essential self-adjointness. So what one tries to do then is to obtain really an Hardy inequality like this one. And there was a result some years ago by Young where he stated to have proven this Hardy inequality with exactly the constant that we would like. So q minus 2 over 2 squared, that is equal to 1 for the Heisenberg group that we are looking at. However, this is false. Indeed, we showed that this this constant can never be q minus 2 over 2 squared. It's always strictly less. And this is obtained by essentially direct computation in this case. So what this tells us is that we cannot apply this technique. We cannot apply a Hardy inequality technique. That is essentially behind this theorem. There are some what is called some Agmon estimates for the solutions of this operator. Let me also observe that we, however, know that a Hardy inequality like this one exists with a positive constant. Unfortunately, this is a result by Lurbach, but it's a result that comes from a much more general setting from metric measure spaces. And the way it is derived does not allow to obtain any direct information on this constant. So we cannot say anything about this constant, except that it's big, that is smaller than what we would like. So this is what goes wrong. So this first observation forced us to dig a little bit deeper and to try to find different reasons for which the result should be true, let's say. And so the strategy we found is the following one. So it's based essentially on a criteria, on an essential self-adjointless criterion that is due mostly to Pavlov and that we just adapted to this setting. And it goes as follows. So we know that our operator, that the operator we are considering is a positive operator, symmetric. Okay, here I'm using the mathematical physics. So I'm taking the minus Laplacian because it's a little bit easier to speak later on. But so this operator is now positive. And so since it is positive and symmetric, it is essentially self-adjoint if and only if this kernel is empty. So there are no L2 solutions to H star plus I equals 0. Okay. Then if you start to dig a little bit deeper on what this means, and you follow what Pavlov did, essentially you see that this means that there are no L2 solutions to a distributional equation, that is this one. Okay. This equation is simply saying that theta, that when you apply minus the Laplacian plus I to theta in the sense of distribution, you get a distribution that is supported on the origin. And then we use that all distributions that are supported in the origin are linear combinations of the Dirac delta and its derivatives. Okay. And then what you do is that you try to directly solve this equation and to show that all possible solutions do not satisfy, are not in L2. And to do that, we exploit the non-commutative Fourier transform on the Heisenberg group. So this is, yeah, we're getting to the short technical part of the talk now. So before telling you how and what is the non-commutative Fourier transform, let me just explain to you the gist of the idea, the gist of the thing in the Euclidean case. So in the Euclidean case, the same thing is true when n is bigger or equal than 4. So I will just focus on looking at the standard Laplacian and at the equation where I just on the right-hand side, I just put the Dirac delta because it's a little bit simpler to manage, but the same thing holds for all the derivatives. Okay. Now, the idea in the Euclidean case is just to take this equation and apply the Fourier transform. So we take this equation, we apply the Fourier transform. You know very well that the Laplacian is diagonalized by the Fourier transform, so it becomes simply the multiplication operator by modulus of lambda squared, and the Dirac delta, that is a sparse distribution, admits a Fourier transform that is simply the constant function 1. So this tells us that the Fourier transform of our solution has to be 1 over modulus of lambda squared plus I. And then what you do, you apply Plancherel theorem that tells you that the L2 norm of your theta is going to be equal to the L2 norm of theta hat. And this one you can directly compute. So you write your integral, you observe that is invariant by rotations. And so you pass in polar coordinates. And you see that you can estimate very easily this integral from below as the integral from 1 to plus infinity of rho to the power n minus 5. So you have n minus 1 that comes from the volume element in polar coordinates and the -4 that comes from the structure of your solution. That is, theta cannot be in L2 if rho to the power n-5 is not integrable at infinity. And this happens exactly when n is strictly smaller than 4. Strictly is bigger or equal, sorry, than 4. So for n strictly smaller than 4, theta is in L2, otherwise it is not. Okay. Now the crucial part, the crucial ingredients in this idea of proof, let's say, is that the Fourier transform diagonalizes the Laplacian, and that we have the Planck-Charles theorem that allows us to transfer the problem of showing that theta is not in L2 to showing that its Fourier transform is not in L2. Okay. So how do we extend this idea to the Heisenberg setting? Now, let me just briefly recall what is the non-commutative Fourier transform in Heisenberg group. So it all starts with a simple observation that if you consider the Fourier transform on Rn, what you're doing is that you are simply decomposing your function f on these phases factors that are e to the power ix dot lambda, and these turns out to be exactly the characters of Rn as a commutative group with respect to the addition. Okay, that is, when you fix lambda, the map that sends x to e to the power ix lambda yields a unitary action of Rn on C. Okay, so one tries to generalize this idea to the Heisenberg group. The problem is that characters turns out that are not rich enough to describe non-commutative structures as the Heisenberg group is. So what you have to do is to delve into the so-called irreducible representations of H1. So you just take this formula, and instead of putting characters here, you put the irreducible representations of H1. And now this is all, this is the basis of non-commutative harmonic analysis. So what you do is that you try to study what are the irreducible representations of the Heisenberg group. These we chose, I mean, there are many choices, but we chose the Schrödinger representations. These are representation that yields an action of H1 on L2 functions of R that is written in this way. It's not very important, the formula for the moment, but the important thing is that these representations are parameterized by a real parameter lambda. Okay, and the Stone-von Neumann theorem tells us that, at least for our purposes, for my purposes later on, these are the only relevant representations. There are other ones, we will ignore them because they are not relevant for the Fourier transform at the moment. And then you simply define the Fourier transform of a sufficiently regular function as above, but replacing the character by your representation. Okay, and what happens is that since the representations are now not complex number but operators, what you get is that your Fourier transform for lambda fixed is actually an operator, and it turns out that is an Hilbert-Schmidt operator on L2 of R. Okay. Now, some properties of this thing is that it is very nice because it diagonalizes the Laplacian. So when you try to compute the Fourier transform of the Laplacian of a function, it turns out that this is the application of a certain operator to the Fourier transform of your function, and this operator is simply the harmonic oscillator with weight lambda. Okay. And then, since we do not like so much to work with operators, we observe that the harmonic oscillator admits an eigenbasis. Okay, it has discrete spectrum. We know explicitly these eigenbases that are the so-called rescaled Hermite functions that have eigenvalue exactly modulus of lambda times 2n plus 1. And so we can decompose the operator f hat along this basis. So instead of looking at the integral the operator integral of f against the representation, we look at the function that depends on lambda, n, and m, that is given by the integral of our function against the what are called the coefficients of our representation x with respect to the Hermite functions. Okay, so from this point of view, in some sense, we are saying that the space, the natural space where frequency lives for the Heisenberg group is the space that I denote here by tilde h1, that is r without the 0 times n squared. Okay, this is the space of frequencies. Compare this with respect to, for example, with Rn, where the frequencies of Rn are exactly Rn, the frequencies of S1, for example, when you do Fourier series are exactly the elements of Z. And here we have something a little bit more complex, okay, but it's still manageable. And then we have, finally, Plancherel theorem. That was the other ingredient we were missing. So we know that our function f on this space, its norm, the norm of f in L2 is equal to the norm of f tilde in L2 when we consider the norm that we're putting on this L2 of h tilde is simply defined in this way. Okay? Very well. So now we have everything to try to solve our equation. So we wanted to solve minus the Laplacian plus I theta equal to the Dirac delta. I recall that the Laplacian is diagonalized as the harmonic oscillator, and that our harmonic oscillator admits the these eigenvectors, these eigenfunctions, sorry, these eigenvalues. That's it. And so we have immediately that the Fourier transform, this delta theta tilde, has exactly this expression. Then the part in delta zero, to transform delta zero, is a little bit more complicated because delta zero is a temperate distribution. So what I spoke to you about before worked just for functions in L2. Then here we have to use some recent results by Baurischmann and Danchamp, where they showed that with these definitions that we gave, our Fourier transform can actually be extended to temperate distribution. And then you can compute exactly what is this the Fourier transform of the Dirac delta, and it turns out that is the identity operator. So it's equal to 1 if n is equal to m and 0 otherwise. Very simple. It doesn't depend on lambda. It's very similar to what happens in the Euclidean case. And then finally, we put everything together, and our equation is equivalent to ask that the Fourier transform of theta evaluated in lambda, n, and m is 0 if n is different from m, and otherwise it has this expression here. That is, again, similar to what was happening in the Euclidean case now. Finally, you apply the Plancherel theorem, and of course here I'm missing the squares. But what you do is simply that you put everything together. You get that the norm of theta tilde up to some constant factor is expressed in this way. And then this, you can you see that you have a lambda d lambda that comes from the Plancherel measure, and at the denominator you have a lambda squared. And so the fact that this is finite would mean that 1 over lambda is integrable at infinity, and this is not possible, so it's plus infinity. And so the solution theta was not in L2. Okay, so this is the idea of the proof of the result for the Heisenberg group. And let me just mention that what happens is that we can localize a little bit this result. And indeed, what we can show is that if you start with an open set with smooth boundary, and you pick a point inside this open set, then the set of self-adjoint extensions of your sub-Laplacian with domain smooth compactly supported function inside this set coincide with the one of the pointed Laplacian when we remove the point. That means that even if we should put boundary conditions to define how the quantum particles evolve, since if we have a smooth boundary, we should put boundary conditions. There is no way around it if we do not put any potential. We, however, do not have point interactions in the interior. And here I just want to say to you a few words, because this is where the Sobolev spaces appear. So for me, the H20U space will be simply the closure of compactly supported function inside the set U with respect to the graph norm given by the sub-Laplacian. And then this H20U is exactly the domain of the closure of the sub-Laplacian inside U, okay? And now to show this theorem, to show this result is exactly equivalent to show that the domain of the closure of the non-pointed sub-Laplacian is exactly the same as the domain of the closure of the pointed sub-Laplacian, because this will imply that their essentially their self-adjoint extension are the same, because every self-adjoint extension of an operator is a self-adjoint extension of its closure. And then to obtain this result, we simply use the fact that the global result I showed you before is equivalent to the same thing on the whole H1. And we proceed by extension, essentially, by extending functions here to function here and extending function here to functions here and showing that they are the same space. Okay, so this closes the question for what was happening in the Heisenberg group, and this is the, let's say, the most technical part of the talk, I hope. And now just let me briefly explain what happens in the general case. Now, in the general case, so I'm just going to consider three-dimensional sub-Riemannian structures. So just to keep things simple, for me, a sub-Riemannian structure on a 3D manifold is going to be defined by a family of smooth vector fields, not necessarily linearly independent, that satisfy the Riemann condition. That is, the Lie algebra that they generate, evaluated at a point, gives me always the full tangent space. And also, I should say, when I define the distribution, so I define the distribution as the span of these vector fields, this distribution should not coincide with the full space, the full tangent space. Then, as usual, I define my flag of distributions. So I start from D, that is the span of x1, xm. I define ds as the iterated Lie brackets up to order s, essentially. And then at any point, I know that there exists some r that depends on q, in principle, such that is the minimal r for which the dr coincides with dqm. That is, to generate the whole tangent space, I need at least r iterated Lie brackets. Now, just to be quick, of course, the Heisenberg group enters into this picture. Here, I just wrote a different choice of vector fields, but it isn't important here. For the Heisenberg group, what happens, as we already said, is that the dimension of the distribution is always 2, while the dimension of D2 is always 3, because with one bracket, we always generate everything. We are step 2 everywhere. On the other hand, we have the structure, for example, like the Martinez space, where we change just a little bit, where we change just a little bit the vector fields of the Heisenberg group, and we obtain a strikingly different phenomenon. So that is that the Lie bracket between x1 and x2 is equal to x dz. That means that if x is different from 0, indeed we just need the 2 Lie brackets to generate everything. On the other hand, if x is equal to 0, 2 Lie brackets are not sufficient. So we need to iterate the procedure and go up to the third step. Okay, that is, in the Martinez case, we have a singular region, that is x equal to 0, where commutators of length 2 are not sufficient to generate the whole tangent space. Points that are not in the singular region are what I'm going to call contact points. Okay. And then we proceed essentially as in the Heisenberg case. So once we have our structure well defined, we can define the sub-Riemannian gradient. By this, here I'm assuming essentially to have picked the metric that makes the metric adapted to this x1, xm. I don't want to specify exactly how to do this right now, but I just picked this sub-Riemannian gradient, and given some smooth measure omega, the sub-Laplacian becomes simply the divergence with respect to this measure omega composed with the sub-Riemannian gradient. Okay, this is a symmetric operator in L2 with weight omega. And you see, in general, we have some terms that are first order terms that corresponds to the divergence with respect to omega of the vector field we chose. Okay. Again, sub-Laplacians are hypoelliptic and sub-elliptic. But here we are not gaining, as in the Heisenberg case, one derivative, we gain 2 over r derivatives. So the higher the step, the less derivatives we gain. And then again, the same result by Strickart says that if the metric structure associated with M is complete and omega is smooth, then our sub-Laplacian is essentially self-adjoint. And our main result is the following. So here I changed a little bit of notation, but okay. So you take a sub-Riemannian manifold defined as before, that is three-dimensional, complete, and endowed with a smooth volume, and you chose a contact point, that is a point where d squared is equal to tqm, then the sub-Laplacian with the domain m minus this point is essentially self-adjoint. Let me just explain to you how the proof goes, because it's nice, I think. So the idea is that since Q is a contact point, we know that to generate the whole tangent space, we just need to consider x1 of Q, x2 of Q, and their commutators. This structure is very specific, is exactly the same structure as the Heisenberg group, and there are very old results on distributions of vector fields that ensure us that if we have this condition, then we can choose coordinates such that D is spanned by the Heisenberg vector fields that here I denote by xh and yh. That is, my vector field x1 and x2 that are completely generic are indeed given by linear combinations that depend smoothly on the point of the Heisenberg vector fields in these coordinates. Now, once I have this, I can use sub-elliptic estimates to show that the norm, the graph norm with respect to the Heisenberg sub-Laplacian that is well defined in this local coordinates. So this graph norm is equivalent to the graph norm of the real sub-Laplacian that I'm considering with the correct volume. And so this shows that the H20 spaces, at least locally, they coincide. Okay, the one defined by delta H and the one defined by delta omega. Finally, we apply the local result on the Heisenberg group that I've told you before to conclude that indeed also the H20 space on M coincide with the H20 space on M without the point Q. And we obtain the essential self-adjointness of delta omega. Here I'm missing, I should have specified that this is the Sobolev space with respect to the volume omega, okay? And now, this was essentially all I wanted to talk about. So just to resume, we proved, what we did in this talk was to prove that point interactions do not exist at contact point of 3D-dimensional sub-Riemannian manifolds and endowed with smooth measures. Now the question is, can this be extended to topological dimensions bigger than 4, so to other sub-Riemannian manifolds? Of course, I believe this to be true, because if it's not true for 3D sub-Riemannian manifold, it shouldn't be true for 4-dimensional onwards, but these techniques cannot be extended to those cases. I mean, we could extend the reasoning on the Heisenberg group could be made on any n-dimensional Heisenberg group, but to replicate this argument in general is not really possible. Also, the result we used to localize everything and reduce to the Heisenberg group is very specific of rank 2 in dimension 3 distributions. So I do not, one has to find a different argument that cannot pass, moreover, through hard inequalities. And solving this case should also help us to solve the problem of singular points, because if we have a singular point, what we could do is to singularize and try to apply the result for higher dimensional sub-Riemannian manifolds if we have that available. And also the other point that I would very like to be closed is, what is the best constant for the hard inequality for the Carnot-Carathéodory distance? We know it's not 1 in the Heisenberg case. Which kind of geometric information it carries? That's essentially an open question right now. So I thank you all for your attention, and I'm open to any questions.
Okay, thank you, Dario, for your talk.
Okay, maybe I will just.
So are there questions or comments? Let me